second. Okay, so we're going to talk fluid force today. I don't suppose you guys have actually in science physics somewhere talked about what a fluid is?
It's different from a liquid.
It's not a liquid. A liquid can be a fluid, but that's not the technical definition of a fluid. There you go, yes. It's anything that conforms to the shape of the container. Yeah, actually, yeah, you may have talked about this more in chemistry than you would have in physics. So, liquids are obviously fluids. What other state of matter is fluid?
Play-Doh. Yeah.
Yeah, a gas will conform to its container. Last time I checked, Play-Doh was not a state of matter.
Yeah, but it forms the container.
Okay, well,
Well, it's not really hard.
what we're out to find is the amount of force a fluid puts on something. Typically, for most of the problems we're going to do today, we're going to talk about putting something down in water and how much force is being applied to it because it's submerged in water. It can be the force on the window of a submarine. It can be the force of, if you have a barrel filled with oil, that oil is applying a fluid force onto the barrel. It can be any of those types of things. I don't suppose there's any hope you actually have studied this before. Okay. So, how does one calculate force? Okay. I am talking this time. I want to talk. Let's take something nice, easy, basic shape. Your nice, normal, rectangular parallelepiped. Okay, so if it's filled with some type of a fluid, I need to know how much force it is applying. We're going to do real simple at the moment. I want to know how much force it's putting on the bottom. Just on the bottom of it, how much force is it applying on the bottom. So, to relate to that, what would just tell me if you're underwater, what's applying force to you?
The water.
The water. Does it matter how far under the water you are?
Yeah.
So when is the force greater?
Underwater.
You are deeper. So obviously depth is going to have something in it. Because the depth is actually going to cause it to flow under. And you have the weight of all that water coming down on you. So therefore, what do we know to help us calculate weight of water? The weight density from yesterday, our good friend Rho that we did. Rho, the weight density of the water is still with us. So, and that's going to, right now I'm going to do it in pounds and feet here. So that's going to give you how many pounds it is per cubic foot. You said depth was going to matter. How does the depth, the more depth you have, the more weight you've got. So yes, you're going to have to multiply by depth. They use depth as h for height. Is that okay with y'all? Okay, so h is depth. So that's going to be measured in what kind of unit? That's going to be feet. And then it matters what kind of a surface you are applying it to. In this case, if I'm doing the bottom of this cube here, then I would need to know, I have to know how much area, I have to say it without giving it away, I have to know the area of what the force is being applied to. So it makes a difference how big the area is as to how much force you're applying. So yes, you then have to know basic area. And area would be in what unit? Feet squared. Now, look, what happens, this is the science people who love their units. What happens when you multiply those units? Yeah. Feet cubed, what are you going to be left with? Pounds. And force is measured in pounds. Pounds of force or newtons of force. So the units work. Any good science teacher will tell you that if you're ever stuck on a problem, you can't figure out what to do, you just start making the units cancel out so you get the answer you want. That can solve a lot of problems without ever knowing the formula. Well, he uses it all the time. Maybe he just didn't spell it out to you. Okay, we are today going to worry about fluid force, but I am going to, for just one moment, there's a difference between force and pressure. Okay? Can any, whoa. It's auto-saving, but probably will take forever. We'll talk pressure here while it's auto-saving. Oh, good, that didn't take so long. All right. Can somebody give me an example of units we use to measure pressures? Somebody said it. PSI. What does PSI stand for? Very good. So, translate into symbols, pounds per square inch is pounds per or over square inches. It could be what else? Say that again. Oh, okay. I was going to actually get to pascals in a second here. You can also do pounds per square foot, depending on if you're working with bigger units. And then actually if you're in the metric system, we would do newtons per square meter. Okay, so what are newtons per square meters? Since you almost gave me that answer a minute ago. That's a pascal. Yeah, okay. A pascal. Pascal was actually a famous mathematician and scientist. And he actually did lots of work with fluid force and pressure and all that stuff. So, why do you guys know kilopascals? What are you using it in? Autos in what? To measure what?
Like it's on our tire pressure gauge.
It's on your tire pressure gauge. Okay, so if you're in metric units, you measure it. Okay. So those are your typical units of pressure. Pressure, the difference here is, notice, it's pounds per square inch. So you're comparing how much force, our force was in pounds. It's nothing more than the force you've got. Square inches, square feet, square meters would be what? What kind of things do you measure with square inches, square feet, and square meters? Areas. So pressure is nothing more than the amount of force you're applying over a certain area. How much area are you applying it to? That's how you get pressure. We really aren't going to do pressure problems. We're just going to, we can calculate the force. You can always get the pressure and divide by the amount of area you had. So we're going pretty much only to the force route. So, it's more physics.
How many babies do we have to do?
52,000.
I would like to go home.
We're going to we want to keep Dylan sitting there watching video forever.
Yeah.
All right. This is a biggie. Once again, same Pascal we were talking about before. Blaise Pascal. 1600-ish. Okay. He's also the guy who really got probability theory rolling. Oh, yeah. Well, they know, you guys know Pascal's triangle. Oh, actually, I need to, Pascal's triangle starts next week. Quinn will be starting to change posters now that we're back in top of grade. Seriously? Really? I believe it. All right, so Pascal's principle. Once again, I don't have a physics background to develop the whole theory for it, but you have to believe me. Okay. What he basically proved is the pressure on an object Am I going to have to threaten you with a seating chart again?
No.
Well, then stop giggling. Mm-hmm.
We're actually talking about physics.
So the idea here is, it doesn't matter, and he actually proves this, of course. It does not matter if you have an object submerged under something. It doesn't matter. Imagine that the ceiling is the top of the water. We are all underwater. And my piece of paper here is, what, 5 feet down from the ceiling. Okay? It does not matter whether I have the paper tilted this way, this way, it doesn't matter how it's positioned. Whatever is at the 5 foot level has the same amount of force or pressure being applied to it. It doesn't matter how it's tipped or oriented. If it's 5 feet deep, it's got the same amount. Which I always thought sounded kind of common sense to me, but to the science people, that's a big deal. So it doesn't matter if it's sitting diagonal or wherever, as long as it's whatever's at 5 foot level, it's going to have the same amount of force on it. Okay. What we did there on the previous screen, when I just defined force for you as being rho times the depth times the area, well, that's all fine, good, and well, if it is something that's nice and level. That's rho, yeah. Sorry. It is a cursive P, because rho is, I'll do it that way. Maybe there's 2 ways to do it, cursive P's. So, when I gave you that one, that force one assumes that it's a level thing, all the forces are exactly at the same on it. Now I want to do things that are in the water vertically, this way, up and down. So now, is the force that's being applied up here on the top of the paper the same as the force that's being applied down here on the bottom? No, because there's more depth. So therefore, and you may remember this on the dam video, they drew you this lovely little picture when they were trying to explain to you how they figured out the force on the gates of the dam. And they said, okay, what we're going to do is we're going to figure out the amount of force on each little rectangle, and then we're going to use letting calculus. We're going to integrate, and we're going to sum up all the little rectangles to get the total, in this case, the total force that's being applied. So it's the same concept. So for us, when we have variable depths, our depths are changing, we're going to change this formula slightly to an integration formula so we can sum up all the different pieces of our object. And, of course, rho is going to have to be in our formula. Your height is going to be, your depth is going to be changing. So I'm going to write this as h of x because it's going to be an expression in x as it changes. Now, it's not going to be a constant 3 feet deep. It's a changing depth. Now, if I'm actually trying to do the force on these little rectangles, I actually need to know area of little rectangles. How do you get area of rectangles? Length times width. Okay. So I'm going to have to know what the length of the rectangle is that's sitting across there, which they write as L for length. What do we always call the thickness of our little rectangle? Dx. Yes, the change in x, how much it changed by. So that would be how the height or thickness of our little rectangles. There's the formula you're going to operate on to do fluid force. That is the formula of the day. And now, since you all came in begging me to please let you memorize the formulas. Oh, yes, sorry. Yes, we would need an A to B. Where would the A to B have to go on the picture? Where would A to B be?
Top to bottom.
Which way? Top to bottom, bottom to top. Top is 0. Depth is top because the top level is 0, and as you go down, it'll actually be A to B, however long the object is. Top is always going to be 0. So it's just like the pump problem that we were just doing. Okay, so now we'll be nice. I'll start nice. No, you really don't have to memorize that one. I will give you this one. However, I am not going to, thank you. I am not going to tell you what the symbols and the formulas mean. I'm just going to slap symbols on the paper. You have to know what the symbols mean. Okay. So